Okay, not forgetting to record. I hope you're doing fine wherever you are. So today, I just uh, uh, I sent you guys the results of quiz 4. So I hope you looked at the email. Um, and you all looked at what you got. Let me show you the. So this is this I already posted the solutions to quiz 4. Um, this is the solution. Um, so I think most of you got this correct, but some of you thought that the some of you thought that the case was IID, which is not. Um, as you can see, as you read the question, it says, assume that xi has the uniform minus theta I plus theta I distribution for I from 1 to k, which clearly means that xi are not identically distributed, right? So this is the case number 3, where you have independent losses, but they're not identically distributed, right? Okay, so that's the only comment I have. So that's the, apart from that, you guys did a great job, and I'm happy about it, okay? Um, okay, and all right. The next quiz is quiz 5, which is this one. So here you have two losses that have a joint distribution with the joint PDF given by this, and the question is to find the PDF and the CDF of the total portfolio loss. So this is stuff we covered last week, you may recall. So this is stuff we did last week. Was it week 5? Yeah, week 5. So if you look, you guys look at the examples we did in week 5, they should help you to do this quiz problem 5. Okay, so which is due next Tuesday, 8th of December. All right, guys, and going back. All right, the stuff we are going to cover today is week 6, right? So this is the week 6 material I'm going to talk about today. So I'll go through these four videos quickly. I hope you guys have already looked at these videos. And then on Thursday, when I see you guys on Thursday, I will go through this problem sheet, which is this one. All right, so this is the problem sheet for Thursday this week. All right. So the topic for this week is financial risk measures, right? So let me briefly go through the material on the videos, right? And so let me change the camera. Just wait a minute. Sorry, guys. Let me change the camera, and here we are. Okay. Hope you can see this. So the first, I will just briefly run through the content of the 4 videos, right? Assuming that you already seen this before. So this is just introduction. So what is a financial risk measure? So it's a loss, for example, I mean, it can mean different things. For example, it can mean a loss associated with an investment, where the variable of interest is the loss associated with an investment. So that's the financial risk. Now, what is a financial risk measure? And again, it can mean different things. It could be, one example could be the probabilities associated with the variable X, right? So if the probability that if the loss is going to be greater than 1 million pounds with probability at least 0.9, then it's not a good idea to invest. Whereas the probability that the loss is going to be greater than £1 million is less than 10 to the power minus 30, which is a very, very, very small number, then maybe it's okay to invest, right? I mean, there's always going to be a probability for this. The question is how large or how small it is, right? So you can think of financial risk measures as measures that give you guidance about whether to invest or not to invest, right? Okay, so that's one thing. I think I talked about this in the videos. I did. I hope you guys watched the video. So this is like a picture about what a financial risk means, or financial. So this is a businessman with a lot of cash. He's trying to cross a river full of sharks from one end to another end without getting, caught, eaten by this. So it's a matter. So there is always a risk. So the question is, how much risk you are prepared to take, right? So that's the and this is another picture, right? And this is another picture, right? Right, and this is the definition of a risk measure. A risk measure is a function from a set of random variables to the positive real line, such that these three conditions must be satisfied. So this is known as the normalized property, where the risk at 0 is equal to 0, as you would expect, right? And this is known as the translated property, and this is known as the monotonic property, which says that you should have two losses. One is less than the other, then the corresponding risks should also satisfy the same relationship, which again makes sense, guys, because if you have two losses with one less than the other, then the corresponding risk must satisfy the same relation, right? I mean, it's just kind of obvious. When you should think about it intuitively, it is obvious, right? Okay. And then there is a definition of a coherent risk measure. A coherent risk measure is something which is, I mean, I'm sure you guys are experts in English better than I do. I mean, coherent means intelligible or something which is good, right? So a coherent risk measure is a risk measure that satisfies these three properties, as well as the two additional properties. So this is known as the positive homogeneity property, and this is known as the subadditive property. The subadditive property is once again, it is kind of intuitive, because what it says that if you have two different investments, right, then the risk associated with the sum of the two investments is less than the sum of the risk associated with the individual investments. It kind of makes sense, right? Okay. Then there are two popular risk measures. One of them, I mean, in this course, I will only talk about two of these, the two most popular risk measures. So suppose X denotes the loss, then the first risk measure is known as the value at risk and denoted by VAR or VAR, and is defined by this equation here. Is the infimum of the set of all U for which the CDF of X is greater than or equal to P, where P is a number between 0 and 1, and this is this CDF of X. And this value at risk is due to the company, I'm sure you guys know, is JP Morgan, which is the big American insurance company, right? The interpretation of VAR is the loss exceeded with probability 1 minus P, right? So for example, VAR at 0.99 has a 1% chance of being exceeded, right, and so on, right? So this is the first, the most popular risk measure is VAR. The second most popular risk measure is expected shortfall, or short ES for abbreviation, and is defined by this nasty looking expression. Don't try to remember this, all right? I will give you a simpler expression later on, where I denotes the indicator function taking these values. I think you guys have seen this before, probably in some of the courses you've taken in the past. So it takes two values, 1 or 0. 1 if A is an event, is true. 0 if A is false, right? And the ES, or expected shortfall, is due to is appeared in the 1990s. It's due to these guys, right? And the interpretation for ES is that it's the average loss. Is the average loss, provided that the loss is less than or equal to the value given by VAR at P, right? So that's the interpretation, right? Okay. The next thing, all right, I've done this, right? I already done this. All right, the next thing is this, right? Because we want the risk measure that is coherent. In other words, we want a risk measure that is intelligible, right, in the real life. So the question is, are VAR and ES coherent risk measures? And this table here answers that question. So there are, as I said, a coherent risk measure must satisfy these 5 properties: the normalized property, translated property, monotony property, positive homogeneity property, and subadditivity property. Unfortunately, VAR does not satisfy all the, it doesn't satisfy the subadditivity property, but ES does satisfy all 5 properties. So ES is a coherent risk measure, but VAR is not. So that's what I've said here. VAR is not a coherent risk measure, but ES is a coherent risk measure, right? Okay. And because VAR has been the most popular, VAR, as I said before, VAR has been the most popular risk measure. And the fact that it is not a coherent risk measure, the fact is it is not a coherent risk measure only came out after the 2008 crisis. You may remember, I think you guys were alive, sorry, not alive, were born at, in 2008, there was a big financial crisis. A lot of people lost a lot of money in every part of the world. And some of the analysts think that this crisis is, well, one of the reasons that this crisis was so big is because the companies used VAR as a risk measure. And VAR, as I explained in the previous slide, is not a coherent risk measure. So they think, like in this article, they are arguing that the use of VAR, the use of value at risk as a risk measure might have caused the 2008 financial crisis, and why it became so global, hitting nearly every country in the world, right? So this, you may want to read this article when you have time. So this, as you can see, the title of the article, "War, the number that killed us," right? So, and sorry, this is, I'm done with this. And then there's one more article here. The title of this article is, "Did War Cause the Crisis That It Meant to Avert?" This is again, once again, about the 2008 financial crisis. And there's one more crisis. There's one more here. This is the US $1 note with the guy, doing this. So did war cause the crisis it meant to avert? It's the same title. And there's one more. There's one more here: War and its role in the credit crisis of 2008, right, or 2009. So all of these all of these articles, they say the same thing. that because VAR is not a coherent risk measure, it might have played a role in the crisis of 2008. And that's why since 2008, you might have noticed that there is a lot of emphasis on trying to develop new risk measures. And in every university in the UK and elsewhere in the US and many other countries, they've developed these master's program in financial mathematics and financial statistics, which is what you are doing, guys, with me. The purpose of these programs, the purpose the purpose of these programs is to I mean, one of the purpose of these programs is try to focus on develop new risk measures, right, that are better than war, right? Okay. Okay. Now, okay. The next thing I want to talk about is, earlier I gave you two formulas, one formula for war and another formula for ES. The formula for ES was very complicated. You may recall in one of the slides I showed you earlier. But if X represents the loss, if X is absolutely, if X is an absolutely continuous random variable, then the formulas that I gave you earlier can be simplified to this and this. So the var becomes the inverse of the CDF at P, and the ES becomes the 1 over P times the integral of var from 0 to P into P, right? Where this is the inverse function of the CDF, right? So these two formulas are much easier to work with than the earlier expressions I gave you, right? But obviously you have this condition that the loss is a absolutely continuous random variable, right? Then I did three examples. This is one example where the loss is normal. This is the second example where the loss is uniform. And this is the third example where the loss is exponentially distributed, right? And then I did the proofs. I mean, this is an important part of the videos. This is where I proved the properties of VAR. Remember, the VAR satisfies the first four of the five properties. It satisfies the normalized property, the translated property, the other two are the monotonic property and the positive homogeneity property. So this is these are the proofs for each case. So for each case, so here I have proved the normalized property, here I have proved the translated property, and so on. So please have a look at these proofs. I mean, if you did not understand my proof, please contact me 24/7. Okay. I hope you guys. I hope you guys understood my proof. All right. So this is the proof for the monotonic property, and this is the proof for the positive homogeneity property. And finally, the subadditive property is not satisfied. And for a proof that this property does not hold, see the course website. And so if you go to the course website, there's a link. There's a link in the course website where I have shown you that the subadditive property is not satisfied for VAR. All right. Okay. And for these are the proofs for ES. So remember that the expected shortfall is a coherent risk measure. In other words, it satisfies all five properties. So it satisfies the normalized property, and this is the proof for it. And it satisfies the translative property, and this is the proof for it. And it satisfies the monotonic property. This is the proof. And it satisfies the positive homogeneity property. This is the proof for it. And finally, it satisfies also the subadditive property, but the proof is not straightforward. But once again, you should go to the course website. You should go to the course website. I've given you a link. I've given you a link where the proofs, where this, the fact that the ES satisfies the subadditive property is proved, right? So please look at the link when you have time. Okay. All right, guys. So these are the contents of the 4 videos on the YouTube channel and also on the course webpage. Any questions you guys have now? I mean, before, what I'm going to do in the remaining time is to do some examples as usual. Before that, I want to ask you if you have questions. Hello, guys. Any questions, guys? Yes, no? Talk to me, guys. No? I mean, any questions on the stuff that I just showed you? I just want to know if you have any questions on. Okay, thank you. Thank you, Scott. All right. So I'm gonna do some examples in the remaining time. So the first example 1. Right. So you so we have loss which assume to have this CDF fx equal to x to the power a, where a is positive. Why should I say that? Sorry, a is greater than 0, and we want to find the 2 risk measures var and es, right? So the first one, so to find remember, to find var, because this is a continuous distribution, we can use this formula. Okay. So what you need to find is the inverse function of the CDF at P, right? So to find the inverse function, so what you do is this: you set the CDF equal to P and solve for X in terms of P, and that will give you the inverse function, right? Okay, so this will imply that and this implies that X all right, so hence the value at risk at P for the random variable X is equal to P raised to the power 1 over A, right? Okay. Now, in order to find the expected shortfall, I'm going to use the formula which I gave you a few slides ago, which is this one. This is the formula I gave you. Okay, right? You may recall this formula in a few slides ago. I gave you this, right? All right. Now we know what var is, so all you have to do is just sub it in here. So this is 1 over p times the integral from 0 to p. This guy here we know is t raised to the power 1 over a dt. Okay. All right. So now integrating this, you get this, right? Yeah. And the taking the limits at p, it will be at p, it will be p to the power 1 over a plus 1 divided by 1 over a plus 1, right? Okay, and at 0, it will be 0, all right? All right, so the answer to the question, the answer to the expression for the expected shortfall is equal to p to the power 1 over a divided by 1 over a plus 1. All right. Okay, so this is the expected shortfall, and this is the expression for the value at risk. Okay. I mean, this is a very simple example. I'm sure you can do it without any problem. Okay. Right. Next, next example. Example 2. Suppose uh, right, so this time the CDF is given by this equation, 1 divided by 1 plus x to the power a, where a is positive. All right. So to find the value address, you need to set the CDF equal to p, yeah, and solve for x in terms of p. So this implies that 1 equal to this, and this implies that x to the power a equal to this, and this is equal to, okay, and this implies that x okay, so hence the value at risk, or var, is given by this formula, 1 minus p divided by p raised to the power 1 over a. Okay, you guys okay with this? Now to find the expected shortfall, at P, use the formula I gave you, which is 1 over P times the integral from 0 to P of var at T dt. Okay, so using this formula, you will get all right. Now this you can write as 1 over P times the integral T to the power this 1 minus T power this dt. Now this is, I don't know whether you remember, or maybe I didn't tell you, I don't know, I can't. You remember something known as the beta function. I did a video on the beta function as the preliminary section of the YouTube channel and also the course website. For the beta function, you have something similar like this, but the integral is from 0 to 1. Do you remember that or not? Yeah. But here, the difference is that you have the same integrand, but the integral is from 0 to not to 1, but to a number p, right? And this kind of integral has a name. This kind of integration has a name, which is known as the incomplete beta function. So I will write it down. The incomplete beta function is defined by the following expression. B, the same notation used for beta function, subscript x, alpha, beta. This is the notation and is defined as follows. 0 to x. Instead of 0 to 1, you go from integrate from 0 to a fixed number x, right? Times t power alpha minus 1, 1 minus t power beta minus 1. So this is exactly the same as the beta function. The only difference is that instead of integrating from 0 to 1, you're integrating from 0 to a number x, which is between 0 and 1. Right? So let me put a box around this so you can see. Okay. All right. Now using this special function known as the incomplete beta function, you can write this guy here as follows. Your alpha will be 1 minus 1 over a, and your beta will be 1 plus 1 over a. All right, so that completes example 2, guys. Yeah, any questions on this, guys? Please let me know. Are you okay with this? All right, next example. Example 3. All right, so here the CDF is given by this 1 divided by 1 plus E minus X. So to find var, you just set this to be equal to P and solve for X in terms of P. So this will be yeah. So you should take the log, you should take minus the log both sides, you will get X is equal to minus log of 1 minus P divided by P. Okay, so the value at risk is minus log of 1 minus P. Okay, all right. Okay, guys. Now, to find the expected shortfall, you integrate, 1 over P times, you integrate the var right? So if you do this, you will get minus, you can pull the minus outside. Then you have log of 1 minus T divided by T dt. Now, any ideas on how to do this integration, guys? I'm sure you guys know integration better than I do. So to do the, I mean, you can do it in several ways. One way is to, all right, split this integration into two. I'm gonna, because you can write log of 1 minus T by T as log of 1 minus T minus log of T, you have two different integrals. The first integral is this one, and the second integral is dt, sorry. Do you see what I've done? I used the fact I split, I written log of this divided by this as log of 1 minus T minus log of T. So you get two different integrals, right? Okay, now to do this integration, you can use parts, integration by parts. And the same thing, to do this integration, you can use integration by parts, right? So let's see what we get. We get, I know integration by parts can be messy sometimes. So here you will get T times log, correct me if I'm wrong, it's possible that I might make some mistakes. All right, so this is the first term, right? The second term, it will be, you have a plus, I think, because of, right? This is what you've got, right? All right, and for the second integral, For the second integral, you will get 1 over p brackets and minus t divided by t dt, right? So once again, if I made a mistake, if I made any error, let me know, please. So this is, so I have applied integration by parts 2 times, one for this integration and one for this integration. So this is by, let me write it down, integration by parts, right? All right, now let's see if we can simplify this. This guy here, if you take the limit at p, you get something, the limit at 0 is 0, so you get p times log of 1 minus p, right? And here, this guy, I'm going to write it in a different way. The integral from 0 to p of, I'm going to write this as t minus 1 plus 1. You see why I'm doing this? Okay. And for the second term, you have plus 1 over p. The limit at p is p log t, and the limit at the p log p. The limit at 0 is 0. The limit at p is this one, and the integral of 1 from 0 to p is p. Okay. All right. Are you guys with me so far or no? Right. Now this here, there are, I put t minus 1 in brackets because if you divide by 1 minus t, you get minus 1, right? Okay, so you get 1 over p times p log of 1 minus p. Now here you have two terms, right? First is this term and second is just the one term. So if you do the integral, you get, correct me if I'm wrong again, but you get minus t minus log of 1 minus t. All right, and then take the limits 0 to p. Okay, this is for the first term. And the second term, you can divide through p, so you get log of p minus 1. Yeah. All right, guys. All right, now let's complete this now. So this is gonna be minus 1 over p times p log 1 minus p. At the limit at p is minus p minus log of 1 minus p. And the limit at 0 is 0. All right, so you have this like this, and then you have log plus log of p minus 1. So it's a lot of calculations, but I mean the calculus is pretty, it's not difficult at all. I mean it's just integration by parts. That's all. That's all you need to know to do example 3. All right, guys, are you okay with this example? Hello, guys, are you okay? All right, I'll just do one final one. So this is example 3. The last one is example 4. The final one, example. All right, suppose x equal to loss as the CDF equal to right, find right. All right, so here we have a slightly different CDF looking like this. So let's first find the value at risk. So you set the CDF equal to P and solve for X in terms of P, right? So which implies that this is equal to P, right? And this implies that X times 2 minus X is equal to P to the power 1 over A, right? So this implies that 2x minus x squared minus p is equal to 0. Now let me multiply by a minus sign so to have it nice. So you have x squared minus 2x plus this equal to 0. Now how do you, I'm sure you know how to solve this equation. So what you have here is a quadratic equation, a squared ax squared plus bx plus c equal to 0. So what's the solution? Minus p, which is 2, plus or minus b squared, which is 4, right? Minus 4ac, which is 4 divided by 2, right? Now, actually, you can simplify this. This will simplify to 1, 1 plus or minus 1 minus p, right? Now, the question is, which of these roots is valid and why? I mean, can both the roots be valid? Um, uh, um, let me think about this. 1 plus not sure, but I think in this case both roots can be valid. I think because when you have 1 plus 1 minus something, which where p is a probability, so you have it depends on the range of x, guys. So depending on the value on the range for x, depending on what range x takes. Let me think. I think excuse me, just give me a sec. If x is 0, x is 1, x is 2. Yeah, I think x, so in this case, I think, yeah, only the minus is valid, because I should have said here, I should have said at the beginning that x lies between 0 and 1 in this case. I should have said at the beginning. So the valid root, root is the one with the minus, right? So it's x 1 minus the square root of 1 minus, yeah. Okay, so the expression for var, is 1 minus the square root of 1 minus this, right? So this is only one part of the answer. Now to do the other part, I think we run out of time, but anyway, let me continue. To do the second part, which is you need to integrate 0 to p of 1 minus square root of 1 minus t. Okay. This integral, to do this kind of integration, you need substitution, right? And well, there are two integrals here. The first one is obvious, right? So this one you can write as the integral of 1 is just p. So it will be 1 minus 1 over p times the integral from 0 to p of the square root of this dt. Right now, to do this, to do this kind of, I don't know whether you guys, maybe you may have a better idea. To do this integration, you need to substitute for this guy here, right? So I'm gonna do the following substitution. Set, say, y equal to this, right? T, this is big T, right? So T will be y to the power a, and dt will be dt by dy is going to be a y to the power a minus 1, right? Put this in a box, right? Then let's see how we can do the integration. If you do the substitution, you get 1 right, and the integration will go from 0 to p to the power 1 over a 1 minus y a y to the power a minus 1 dy. Okay, so this will be, I'm sorry I ran out of time, but I hope you are patient enough to wait for me to finish this, right? So this is 0 to p to the power 1 over a square root of 1 minus y to the power a minus 1 dy. Now what you have here is precisely what I said before in one of the early examples. This is an incomplete beta function. Instead of from 0 to 1, you have 0 to a fixed number. So the final step of my answer is This is an incomplete beta function finishing at this point. Yeah. And your alpha will be A, and your beta will be 3/2. All right, so this is the expression for the expected shortfall, for example 4. I hope you understood what I did. I just made this substitution. I just made the substitution for this guy here, right? And you get this integral, and this integral here is exactly the incomplete beta function I talked about earlier, right? All right, guys. Any questions? Any questions? So I'll see you guys on Thursday. You know the problem sheet that we need to go through. So so you know what I'm talking about. I mean, the problem sheet that you need to go through on Thursday is the one I showed you earlier. Is this one? Yeah, is this. This is the problem sheet you will need to go through Thursday. So please try to have a look at some of these questions, okay, before Thursday. All right, guys. So have a great day. Have a great evening or afternoon or wherever you are. I'll talk to you guys again on Thursday. And if you have questions before that, yes, contact me 24/7 by email or Skype or Zoom or whatever. Okay.